So let me read one question. So one question from Anand Muttaya is there a possibility to form some polymer before forming crystal? Is there a possibility to form some polymer before forming crystal? Okay, so you are talking about in solution. So in solution, this kind of chemistry, you need, for example, a very high temperature. This particular reaction, Azide-Alkyne cycloaddition reaction is possible, as I said, that's called Huygens reaction. You need very high temperature, like 150 degrees centigrade. Then they will undergo cycloaddition. You can get oligomers, but you will not have selectivity. You will have a mixture of 1,5 and 1,4, as I said. And you will have some oligomers only. And usually these kind of molecules undergo cyclic derivatives and you don't get polymers actually. So polymer formation is not possible. And copper catalyzed one can use, but in that case also sometimes you get cyclic derivatives when you use this kind of chiral molecules, which has a turn actually. So that is the answer. So the next one is Pravad Kumar Swain. Is there any steric effect in the polymeric compounds containing azide or triacyl derivatives? Steric effect in polymeric compounds containing azide. So I understand this question as does the steric play in the polymerization of the monomer? Of course, yes. It is important that there should be, when this azide and alkane react, these monomers are coming closer to some extent actually, if you maybe a fraction of angstrom actually closer, because a non-covalent interaction or non-covalent bond is becoming a covalent bond. So there should be some kind of movement or motion, either whole molecule or part of the molecule. So if there is sterically, it's blocked, that's a problem. So in such cases, it cannot happen. So there should be room for such a movement. Yes, steric has a role. Aditi Jain, were the crystals stored in a desiccator when kept at room temperature for a month? Could the atmospheric condition have affected twisting that you? No, so we did not keep at a desiccator, just we have kept in the flask. Even at a fridge we have kept, we can keep it open, no issue. So these are really stable molecules, stable crystals. So we did not keep in desiccator actually. Could the atmospheric conditions have affected twisting that you observe? I don't think in this case, because we have clearly studied the mechanism of that twisting in that PNAS paper. So it is there is a strain which is developed because, as I said, molecules have to move. And when molecules move in the crystal, that generates strain in the crystal actually. So there is a packing change that generates strain. And to reduce the strain, the whole crystal undergo twisting. But the direction of twisting is decided by the chirality of the molecule. Anand Muttaya asked if the side chain length is increased like anthracene, can it absorb more water? Thank you, sir. Yeah, actually, that is a difficult question to answer. We don't know unless this happens, right? So even in our case, whichever compound which has taken water, we did not predict whether it will take water. So in that, what happened was during the reaction, there was some space created because of the movement of this azide and alkane. And there is a nicely hydrogen bondable triacyl nitrogen. So usually crystal doesn't like empty space. So crystal usually want to close back. So if there is something, that's why sometimes when you crystallize some material from solvents, you have solvents also, right? So that is to close back. So in this case, they don't have anything else other than atmospheric water. So they take water, and since there is a nitrogen which can nicely hydrogen bond to that, it takes water and it makes a stoichiometric water, 2 molecules per monomer unit. So it's difficult to predict if you have a bigger molecule like anthracene, will it take more water? That one has to see, because there should be not just space, also this kind of interaction which holds this kind of water molecules. So that a priori prediction of such things will be difficult as of now. Manoj Kumar Pradhan, did you check the thermal stability of triacyl linked DNA? Of course, we checked, we did TGA, I mean, simple thing is TGA, right? It is stable up to 400 degrees centigrade. That's quite stable. So triacyl linked DNA is more stable than the normal DNA, of course. That is expected because phosphodiester linkage is not that stable compared to a rock like triacyl linkage. We have studied that. They are stable. Next one is analog. So this is an anonymous attendee actually. Okay. So why 1,4-triacyl synthesis you planning not 1,5-triacyl? Actually, we have done both. Again, in this case, we cannot clearly predict which of the triacyl will be formed. Topochemical reaction will give specifically one, usually get specifically one product. But now between 1,5 and 1,4, it's too much of precision. That much precision at the monomer level planning is difficult as of now. We have tried, we have succeeded in some cases, we have not succeeded, we have failed in many cases. I mean, if I want to make 1,5 and we design molecules for 1,5, sometimes we got 1,4. So there is a very little difference between these two, right? So it's between parallel or anti-parallel. And if there is a slight motion, that can go to the other form. So crystal behaves, always will not behave the way we want it. So there is not much success we can say in that. But definitely, of course, you will get a triacyl link and that will be specific. But between 1,4 and 1,5, it's tough as of now. What is the use of triacyl polymers? Of course, triacyl polymers are, for example, in the sugar case, you are getting a polymer which cannot be hydrolyzed by enzymes. For example, starch or cellulose, our cloth. After some time, you see that the cotton cloth is getting torn, right? It's getting disintegrated. That's because a lot of environmental bacterial enzymes are the glycosidases enzyme, which can cut this polymer chop into polymer into smaller oligomers or even to monosaccharides. So these are called glycosidases. A simple example I'm saying. Now, once you have this kind of non-glycosidic linkage, like triacyl linkage, they are rock-like stable linkages. They cannot be cleaved by enzymes, so they are much more stable. So you get fibers, for example, instead of cellulose fibers, you get this kind of artificial fibers, which are much more stronger than cotton, for example. This is just an example. So they are stable, more stable. And also I have shown you some material which can take water. And now currently we are thinking of really practically doing this water harvesting in collaboration with some other people. And also we have some new result which I did not show you, which can take very high load actually. So that's such a strong materials we can get because of this particular linkage. Bijoy Day, very nice talk, sir. My question is, in the case someone wants to utilize this TAAC reaction with metal ligand assembly, metal complex, for different properties due to polymerization, what strategy should one take? I could understand that free acid hydroxyl group is good, or there is hydrogen bonding network, but this group may interfere with metal centers. So if the hydrogen bonding is not present as such, then how one should approach to get Azide-Alkyne in close proximity? That's a very good question, and we have done this one. We have not published that yet. So we can make complexes with on the ligands. We can have this Azide-Alkyne, and again, what we do is we rely on this CCDC search actually. So we see similar complexes, reported structures. All of them have this position of ligand most of the time constant. So in that ligand, we make alterations wherein we put Azide-Alkyne. Then they can be proximal in the crystal lattice. Not all the time again successful. So we had one failure and one success, and we are yet to publish that. So that's we are doing. You're right. Usually we need some directing group, hydrogen bonding or halogen bonding, etc. Otherwise, it's tough. Sometimes it's a luck, actually. Luck plays a role in this. If you're lucky, you will get the right orientation. Otherwise, there is high chance of failure in this case. Professor Ratnesh Das is a friend of mine. So thanks, Professor Kana. It was a wonderful scientific presentation packed with very interesting studies. I have a very simple query. What is the function of a base in copper UAC click reaction? I think you have to make this acetylide, right? So the mechanism, if I understood correctly, it's copper from a copper acetylide. So you have to deprotonate that CH actually. So that is the use, I think, for a base. So that will deprotonate, and then copper can form a copper acetylide. And then the other azide also will come in complex, and in a fashion that it will form only one 4-linked triacyl. This is my understanding. Are you, anonymous attendee again, are you using these polymers for fluorescence in cell culture? Are you using polymers for fluorescence? No, we have not thought about that. And none of our compounds have fluorescence. We have not studied. Maybe possibly that DNA derivative might have. If you have 2 amino purines, they are fluorescent. But we did not study these fluorescent properties of these materials. Is this polymer biodegradable? Actually, we haven't looked at that. For example, the linkage which we are making, that is not biodegradable for sure, the triacyl. This is what I have answered in the previous question, actually. But as you know, we have our monomer itself is a peptide. Peptide means dipeptide or tripeptide. They have normal peptidic linkage. Only at the end, we have azide and alkyne. In between, you have 2 or 3 amide linkages. These amide linkages are cleavable by proteases, enzyme called proteases, or proteases, you can say, or peptidases. So it should be possible to biodegrade using these proteases, for example. And also, if you have sugar connected with normal glycosidase linkage in between, yes, they are also possible by glycosidase. But we have not checked this aspect because our interest was not that. We have not studied that. Good work, doctor. Thank you very much. Maybe this is Apurva Konar, okay. Wonderful chemistry, Kana. Yeah, he's my friend, of course. Congratulations to you and your team. Is there anything known about biological activity of pseudo DNA, such as binding protein? Yeah, of course. Yes, this unnatural, this pseudo DNA people have made in using solution phase chemistry. A Japanese team, Isobe and team, they made only 10-mer. And they made only homobasic, exactly the one we have made actually, with cytosine as a unit. So they made 10-mer of cytosine, and they shown that the complementary natural DNA can bind nicely and better than the normal DNA actually. So this binding, this hybrid DNA with complementary normal DNA is much more stronger. And they also have shown that they can do this kind of thing in silencing in the gene, for example. So it's possible. Only issue is that the solubility is really poor here, unlike the natural DNA, because when you have triacyl motif, their solubility goes really bad. That's why you could see only up to 10-mer in the multispectrum, though most of the polymer we made are insoluble. So that's why they also could make only 9-mers to show their biological activity, the Japanese team I'm talking about. Dr. AVR, what are the practical uses of these polymers? I think I have answered this before. Of course, water harvesting and also stronger fibers, etc. These are some of the possible applications. Shubhankar Maiti, what is the application of this polymer or the crystal? This again, I answered same question as the previous one. How temperature can help in cycloaddition reaction in your study? Of course, this is again Prabhat, again another friend of mine. So Prabhat, yes, temperature can. Of course, this is a thermal reaction, thermal cycloaddition reaction. Higher temperature, they'll undergo reaction faster. But the problem is we cannot heat them at high temperature. Once we heat closer to the melting point or at the melting point, it will melt. Then we cannot heat these crystals at a very high temperature. Some crystals, if they have high melting point, they can be heated, and we have shown that yes, at high temperature, of course, they are very, very fast reaction. Abdul Salam, thank you for wonderful lecture, sir. Is it possible for polymer formation in copper CuCaC reaction at room temperature? No, this I have answered. These kind of molecules wherein they have a natural curvature. For example, we are taking the peptides or sugars. They usually undergo cyclooligomerization. You get a cyclic trimer, tetramer, which people have made and they have used as a host for a different gas actually. All these kinds of molecules. In solution, you get cyclic oligomers, trimer, tetramer, pentamer, a mixture of them. So you cannot make polymer in solution. Click chemistry polymer using these monomers. That is a problem, and that is the advantage of our chemistry in this case. Dinkar Sahal, why did nature never use alkane azide reaction to make its polymers? I think alkane azide is not there in the natural system. As alkanes are of course there. I don't know any natural system having azide. These are man-made thing, and I don't know whether nature is in the process of making this, because for nature to make anything, it will take billions of years, right? So if they find it better, they might evolve. So I don't know answer why nature is not making, because there are no biosynthetic pathway to make this as of now, but they can evolve in principle in billion years or so. Yan Shalvakumaran, thank you for your valuable information. What is the major application of your molecules? This is a question which has been answered multiple times. Prabhat, again, nice to hear you after some months, of course. Nice to see you online after so many months. Why did not absorb carbon dioxide instead of H2O from atmosphere? This again, I have asked Manojit Das asked this question. This is because the nitrogen, the triacyl nitrogen had a nice hydrogen bonding with water. That is not possible in carbon dioxide case. So that is the reason. So there is a specific interaction, that hydrogen bonding interaction, which made it specifically water molecule. The next one is by Dr. Usharani RK. Dear Professor, thank you very much for your very more informative presentation. I wish to know the basic main strategies one should adopt while performing this type of synthesis of biopolymer mimics. I think I have answered in multiple ways actually. So this is, we are designing monomers in such a way that they have to be proximal. So we essentially do something called crystal engineering. So we engineer the crystal, and I always don't think that always it is successful. Whatever we present, it is only success stories, right? Usually that is the case. Any speaker will present only the successful cases. So there are many failures also. So we also find failures, but more success than failures. So we use crystal engineering for this. What is the interchain distance of polymers? So that is different for different polymers. Actually, it's a few angstrom actually. So if you're specifically asking something, I have to go back and see. It's in few angstrom actually. This polymers are static or dynamic. This polymer, I don't know what you mean by that. So do they move in the crystal? They don't move in the crystal once they form. They are static actually. They can be dynamic once you make them into solution. Of course, you can make them solubilize. I think if this is not answered, I do not understand your question very well. I think this is what you have asked. Okay, so you answered that, anonymous. Yes. So I think that's all we have questions so far. I have answered all of the questions so far.